So welcome again. It's Friday, and I'm very pleased that our subject today is very interesting. It's about the making of solar systems. My name is Christian Sasser. I'm the astronomer in charge for iTelescope. And this is going to be really interesting. Our guest today is called William Balmer, and William Balmer is a PhD student, and he's also a freelance science journalist. And you really notice that when you talk to him. He's originally actually from Portland, Oregon, lovely Northwest coast, right? And he misses that. And at the moment, he is at the Hopkins University, continuing with his PhD. And interestingly enough, he also conducts research at the Space Telescope Science Institute. So without further ado, William, welcome.
Thank you so much for that introduction, Christian.
Very nice.
It's really great to be here. Yeah. And I'm super excited to get to talk today. I think I'm most excited to get to try and elucidate some of the, places in the universe where amateurs can really target the process of star and planet formation to create really beautiful images and hopefully teach you guys something along the way.
Absolutely. Well, we are really delighted to have you. So without further ado, please start, and I'll launch the polls when you're ready. Okay.
Great. All right. Sounds good. Okay. Here we are. You can see this screen share okay?
Yes, it's good. It's good. Thank you.
All right, wonderful. Okay, well, thank you again for having me. Like you just heard, my name is William, and so I'll just get right into the talk about the process of star and planet formation or making new solar systems. So just a quick roadmap of the talk. I'm going to try and lay out some of our expectations for how star and planet formation might occur based on our observations of our own solar system and our observations of exoplanets. And then I'll try and walk you through some of the steps in the theory of star and planet formation. And then I'll go back and show you all of the cool observations that back up those steps in that theory. And then I wanted to end, because I do work at the Space Telescope Science Institute and I work on the JWST NERCAM team, I wanted to end with showing you some of the latest results from that particular bucket of bolts that are informing our understanding of star and planet formation. So to get started, what are some of our expectations for how solar systems form in the universe? So in our own solar system, we have 8 planets or 9, depending on who you're talking to. We have these 4 rocky inner planets, and then we have 4 icy and gaseous outer planets. And we also have a ton of smaller minor planets and asteroids and comets. But the big planets, the 8, all orbit on nearly circular orbits around the sun, which is an interesting coincidence. And they all orbit in effectively the same plane, which is relatively aligned with the sun's rotation. So we call this the ecliptic plane. And if you go out at night and you look for planets, that's where you're looking for them. So the first poll question, actually, that I'll have Christian boot up is, what do these observations imply about star and planet formation generally? Or do they imply anything? So there's the question, what does the size and composition of the solar system planets imply about planet formation? You have a couple of different options. And with any of the poll questions that I ask you today, it's okay to just take a complete guess, because hopefully by the end of the talk, you'll have the answers to nail these questions for certain in the future.
And I can say, William, they're not easy, right? If you're not.
No. So
I really, I was really thinking, so don't feel bad if you
don't stress out. Yeah,
please.
Exactly. You're not in school anymore, or maybe you are, but this isn't high stakes.
Okay, we'll take a few more seconds and then I will share the results. What do you think, William?
Ooh, okay. So we've got a couple answers but people seem to have converged on B, which is the planets formed from a thin disk of material that once orbited the sun. And this is the correct answer.
Wow.
So good job, everyone. So perhaps the planets formed from a thin disk of material orbiting around the sun. But the real question is, how do you get that kind of structure around a newly formed star? And we'll learn that later. And then perhaps also there's, the material in that disk is hotter closer into the sun. And so there's less icy material close in and more icy material far out. So that's maybe why you see rocky planets without big envelopes of gas and ice further in, and then outwards you see planets like Neptune and Uranus. So these are some things to be thinking about when we try and create a model for how solar systems form generally. But in the past 30 years, we've also been able to go out and make measurements of exoplanets, or planets orbiting other stars other than our sun. And these have really dramatically reshaped our understanding of what we think is possible in planet formation. So what are the possible outcomes of planet formation? The first planet that we ever discovered, 51 Pegasi b, was a planet about half the mass of Jupiter, but it orbited its star super, super close in. So even closer in than Mercury orbits the sun. So we call these hot Jupiters, and they're very tricky to explain with a generalized theory of solar system formation. There are also these objects called mini Neptunes, which are planets discovered during the Kepler mission. And these are, halfway in between sort of the mass of the Earth and the mass of Neptune, right? We also observe planets on non-circular orbits, which is interesting. So we see in this movie here a direct image of the planet 51 Eridani b, and it has a similar mass to Jupiter, but unlike Jupiter, it orbits its star in an elliptical orbit. So you can kind of see here, it's not quite orbiting in a pure circle, it's moving inwards as it's orbiting closer to its star. When we look at exoplanets on sort of a population level too, we can notice some trends. So when you look at the number of planets versus the mass of those planets, say you just make a histogram like this one, even though this is a fairly old result, this still holds up even with missions like Kepler and TESS discovering thousands of new planets. We see a lot more small planets, less massive planets, than we see more massive planets. So in general, we see a lot more planets like Neptune than we do Jupiter, per se. We also observe, and this is an interesting sort of nuanced thing to discuss, but we observe more giant planets around what we call metal-rich stars than we do around metal-poor stars. So this is a chart of what's known as the metallicity of a star, the ratio of iron to hydrogen in the star's atmosphere. So a smaller number here is a lower ratio. As you get up here, you're adding more and more iron into that star's atmosphere. You can see the number of stars with planets dramatically increases as you increase the number of, the number of metal atoms within that star. So this is, like I said, it's a nuanced and sort of strange thing, but it's something that we have to explain with our model, and we'll get to how we explain this later. And it is kind of intuitive when you learn about it. So we now have over 5,000 exoplanets that we know of. I'm plotting here the distance between these discovered planets and their host star versus their mass. And here you can see the solar system planets. And although our detection methods for discovering new planets are very biased, you can see we haven't discovered a lot of solar system analogs. We need to explain all of these weird things with whatever generalized theory we come up with, right? So we need to be able to explain both the solar system and all of these new discoveries. We also need to explain how stars form, right? So star and planet formation are both very intricately linked. One follows from the other. But luckily, we've been observing stars for, more than 4 millennia. we've been observing them very detailed, with instruments and modern telescopes for the past 200 to 400 years. So we know a lot about them. And some back of the envelope physics can tell you that the most important parameter that you can use to describe a star is its mass. This is because stars are governed by gravity, right? They're so massive that any other effect that you can describe is less important than just the sheer weight of inwards force crushing them together. So more massive stars are brighter and hotter, and they burn hydrogen faster. Those are all interlinked because all of that gravity is crushing hydrogen atoms together to fuse. That process is releasing a lot of heat, which generates a lot of light, right? And because they're burning hydrogen faster at their cores, they live for much shorter periods of time before they go supernova or evolve and become white dwarfs. On the other hand, less massive stars are much dimmer and cooler. They fuse very slowly, and so they live for a very long time. We also know a lot about the distribution of stars in terms of their mass throughout the galaxy. It seems to be relatively constant if you go to the middle of the galaxy or you go out to the spiral arms of the galaxy. And it seems to follow this general distribution where there are more smaller stars or less massive stars than there are massive stars until you get to about this turnover point at around 10th the mass of the sun. So there's this distribution of stars. There's very few bright blue stars and a lot of sun-like stars and even more red small stars here. You get to this turnover point. Well, so the most common star here are called M dwarfs. You might have heard of these. They're these small, dim red balls of gas. But we don't know too much about what happens after this turnover point. So these are objects called brown dwarfs. And after about 1/10 of the mass of the sun, these objects don't have enough gravity to actually ignite nuclear fusion at their cores. So there seems to be less of them in the universe. So maybe the universe is preferentially creating less massive stars up until this point where they cease to become stars, and then this distribution tails off. So to overview, I guess, our expectations going into trying to make a model for star and planet formation, we have to make sure that there are planets of all sizes at a wide range of distances from their stars. We need to make sure that there are much more small planets than there are big planets. We need to make sure that there are many more small stars than big stars. We need to ensure this weird nuanced thing where you see more planets around metal-rich stars than metal-poor stars, and you should probably end up with fewer brown dwarfs than small stars. So the next poll question relates to this middle point here, that there are more small planets than there are big planets. And like Christian said, this is a tough one. So give it your best guess, but you won't be held to your final answer because we'll learn why this is the case in a couple slides.
Yeah, William, whilst you're at it, I'm just telling people, because I think they were a bit confused. It's one question about the ratio of the iron ratio, why it's negative, and then I think people are not always used to the logarithmic scale.
Yes, yeah.
So maybe you could just explain that, right?
Totally, yes. So
Yeah.
astronomers love logarithms. You can see that even in this plot here, where instead of plotting just the mass of the star as a linear number, evenly spaced across the plot here, what I'm actually showing is the logarithm of the mass, which behaves, anti-exponentially. You could think about it that way. So similar to that in the case over here, where we're talking about this ratio of iron to hydrogen atoms. This is a logarithm, but it's a ratio of 2 logarithms. So really the thing to know about the log scale is that when you have very small numbers, those numbers will be negative. When you have a number around unity, it'll be 0 in the log scale, and when you have a number greater than unity, it'll be a positive number here.
Okay, I'll share the results
Yep.
now. 1 second, where are we? No, what happened to the polls? Here we are, share results. Yeah.
Okay. Okay. This one was harder. So the options were, how do you make more small planets than big planets? So 11% of people said big planets take longer to make, and solar winds blow away planet-making material. Then 18% of people said big planets are broken into smaller planets by collisional fragmentation. 11% of people also said it's difficult to make small planets bigger, so very few small planets can ever become big planets. And then 61% of people said both A and C are correct. And this is actually the correct answer again. So good job, everyone. We'll see why this is, like I said, in a couple slides.
That's quite impressive, I think.
Yeah, everyone has a pretty good intuition, I think.
I think so. Okay.
All right. So let's get into the theory of solar system formation. So first off, where does solar system formation happen? So star formation happens in these dense spiral arms of the Milky Way. And I like to think back to this traffic diagram when I understand why this is. So if you have a really slow moving truck on the highway, right, you often will see a knot of cars and of traffic following that truck, because the cars all want to move faster, but they're impeded. Their way is blocked by the truck. They have to slow down or change lanes to move around it. And so as the truck itself propagates, you see this overdensity propagate with it, even though the cars are still moving at their own speeds here. So the similar thing is happening with these overdensities of stars and gas and dust in these arms of the Milky Way. So as these spiral arms of stars move throughout the galaxy, they carry with them this overdensity, and that causes them to sweep up these big knots and clouds of molecular gas. Here you see them. And then those clouds, as we'll see soon, condense down into newly formed stars, which sort of pop out on the other side of this spiral arm region. And you can actually see that in this image here on the left of a spiral arm galaxy, where you can see these dark ridges and sort of brownish features. Those are the dark molecular clouds, these overdensities of gas and dust. And then these red sort of fireworks along the edges here, those are star forming regions where new stars are being born. So in general, within a galaxy, you'll have older stars near the center, and then out in the spiral arms, you'll have new regions of star formation. So star formation happens in these giant molecular clouds. And when these clouds become so large that they can't support their own self-gravity with their gas pressure, they collapse inwards. So you can see simulations of this, where if you just throw in into a computer, you type up some physics, and then you simulate a big ball of diffuse gas, and then you just let it go throughout time, like we see here. It condenses down into these filaments and these nodes. And as time progresses, the cloud is contracting. It's growing in density, and therefore putting more star-forming material closer to itself. And if it zooms in here on this, sort of the densest core of the cloud, we can see what starts to happen, where you have large pockets of gas begin to form circular, massive protostars. These protostars, as they're forming, fling around each other. Some of them are even, you can see the beginnings of disks being captured around these. And because of that complex and chaotic dynamical environment, these clouds contract, and then they fling all of their stars out into the spiral arm of the galaxy. So this is a rather simple simulation from about 15 or so years ago now. Here you can see, another one of those knots, just all of these stars And because they're in these chaotic orbits around each other, they just fling each other out into the galaxy and populate the galaxy with newly made star systems. We'll go now to a much more updated simulation from only a couple years ago. And instead of just gravity versus gas pressure, this simulation includes a bunch of very fancy and fiddly physics. So, when the new stars form, they'll ignite their own hydrogen fusion at their cores, and that will cause little outbursts that you see throughout the simulation. When stars collide, they can, erupt or shear, and so you'll see lots of complex dynamics happening in this cloud. But the overall concept is effectively the same as what we just saw, right? Big cloud is disturbed and contracts under its own self-gravitation until the gas crunches itself down into a newly formed star. And then you can start to see, as those stars ignite their hydrogen fusion, these huge outbursts of material from them. And the reason this is important to simulate is that these outbursts from these, massive stars that form can actually go on to disturb the rest of the cloud and almost like a cascade effect, start the formation process for other smaller bits of material that will go on to make small stars. So this was a really lovely simulation from the StarForge collaboration. And now they're just sort of showing off how good their simulation was by panning around it and doing all sorts of cool zooms effects. So I mentioned that you can have events that trigger the collapse of these giant molecular clouds. So there are a handful of processes that are theorized to be efficient triggers of star formation. So the most self-explanatory one is self-gravity, right? If you have a big diffuse cloud and it gains enough mass just by sort of sweeping throughout the galaxy and gathering up lots of tiny particles, it'll eventually grow to a size where it will be unstable and collapse inwards due to its own gravity. But there's also, before that could happen, there could be turbulent effects. If parts of the cloud are moving at different speeds, you can have shearing between, sections of the cloud that can cause it to become unstable. You can imagine if there's a nearby supernova that explodes, its shock wave reaches a molecular cloud and pushes part of the material inwards, that material can become unstable and shrink down to create new stars. And there are even more complex effects, like what if one part of the cloud has a magnetic field, and so it distributes energy and angular momentum along those magnetic field lines to other portions of the cloud. But in general, you have this effect happening at a lot of different scales, right? So you have the big molecular cloud here, which is maybe 60 light years across. And within that, you have multiple filaments of gas and dust collapsing in on themselves that are maybe 6 light years across. And within each filament, you see these dense cores. And if you zoom in on a single dense core, that's where you're getting a new solar system being formed. Right, so this is what we call a young stellar object when they're in this state. And this can happen fairly rapidly when we think about, I guess, timelines within the universe. So this whole process can happen in 10 or so million years, right? Whereas the solar system has been around for billions of years. So once these dense cores start to form, you're now on the scale of an individual solar system, right? All of the material that's within that dense core will eventually go on to create the solar system. So these dense cores, they slowly contract under their own self-gravity. And as they're contracting, all of those atoms are being put into closer and closer proximity to one another. So they're bouncing around against each other. And those collisions generate heat, right? So when you compress a gas downwards, you increase the temperature of the gas. You'll do this to a point that the center of that dense core is dense and hot enough to ignite nuclear fusion. And once you get to that point, then you have a star. So you can imagine you're contracting your core down, and it's getting hotter, but it's also speeding up. It's rotating more rapidly. And I like to use this analogy of a figure skater to explain. But if you imagine that your dense molecular core is a big figure skater with their arms out wide, as you contract that core inwards, right, as you shrink the scale, in order to conserve angular momentum, you have to speed up the rotation. So as this protostar compresses, it spins faster and faster. So what you're left over with at the center of these cores is a newly ignited protostar that's very hot and spinning very fast. I'll show the video once again to illustrate this effect. So this is just conservation of angular momentum. So as this new star spins, it has rapidly collapsed from a cloud that's multiple light years across to a size about a few times the radius of the sun. And all of the gas that doesn't make it onto the star is spinning very fast too. So you have a new star at the center, which is blowing material outwards because it has all of that new heat and light from its hydrogen emission. And so you reach a sort of hydrostatic equilibrium phase where the rest of the gas that was left over wants to flow inwards due to gravity, but it's being pushed outwards by all of the light and the heat from the newly ignited star. So this is an illustration of that. So what happens to the rest of this residual material, right? It can't fall onto the star because all of that radiation pressure is now keeping it buoyed out at this size here. But it's still in orbit, and it's still orbiting very fast around this newly made star. So if we examine the sort of forces that this cloud of gas feels, right? It feels this gas pressure out in all of the directions. But it also feels this centrifugal force in a preferential direction. It's spinning very fast, and you can imagine the force you feel when you are driving your car and you make a sharp turn. That force sort of pushes you out to one side that's opposite to the direction that you're turning in. The gas is feeling that force on top of the gas pressure. And these two forces are fighting gravity, which is pushing down in all directions. So what happens over time, right? So you have the gas feeling this smaller force in all directions, and then a large force in one particular axis. And over time, this causes the gas to flatten out into first an oval and then into a disk. So what you're left over with is a newly formed protostar. And then because of this difference in the forces that the gas is feeling due to its own rotation, you are left with a protostar and a disk surrounding it. So this disk can then help add new material to the star. Bits of the inner disk can fall onto the star more easily. But important to our story here is that the disk is the site of planet formation. And it's that disk that we theorized about at the beginning of the talk, where we saw all of the planets along the same line, all orbiting in the same plane. We thought, okay, well, maybe they formed from some disk. Well, it turns out it's very easy to explain why that is just by considering classical mechanics and the conservations of angular momentum within a collapsing prestellar cloud. So this is great because this concentrates all of our planet-making material into one place, and that makes it much more efficient to form smaller bodies around this newly formed star. Yep, so I just spoke about this point. So if we zoom in into that disk, the disk is settling down into what we call the mid-plane. And you have a bunch of gas. Hydrogen gas is the most predominant element in the disk. But embedded within that hydrogen gas are all these small specks of dust and other elements. And these specks of dust in this soup of hydrogen can start to stick together as they collide with each other and grow from dust into pebbles, and then from pebbles into boulders. And you can see where this is going, right? From boulders into what we call planetesimals. So these planetesimals are the building blocks of planets, but they start at a very, very small scale. You can see a few microns wide with these small dust grains. Because you put so many of those dust grains that were in this big cloud into a very thin region of the disk, you're able to get a number density of them that's great enough that these collisions become very probable, and you can start building up these building blocks. So this explains actually why there are more planets around metal-rich stars. And that's because metal-rich stars form from metal-rich clouds, and therefore have metal-rich disks. And if you have more metals, that means you have a lot more of this, these other elements other than hydrogen and helium. And that means you can form more pebbles, which means you can build more planetesimals, which means that in general, you can create more planets around these metal-rich stars. So if you have a very metal-poor cloud, you won't end up with as many planets at the end of your process as if you started with a metal-rich cloud. This is interesting to think about in terms of the history of the universe, right? Because the universe started out with just hydrogen and some helium. And you had to start to build up those metals through generations of star formation, right? So stars fuse hydrogen into helium, and they fuse helium into heavier elements at their cores. And then those stars explode into supernova, and they enrich the rest of the universe with those metals so that the next generation of star and planet formation has more to build with. Hopefully this is how humanity works, but that remains to be seen too. So the outcome of this planetesimal formation, it appears to be these, planets about the size of Mars, right? And that's when you run a bunch of simulations, that appears to be the sort of characteristic size that you sort of top out with. And in order to make much bigger planets, you have to take these Mars-sized rocks and you have to cross their orbits and get them to collide, right? So you have this sort of bottom-up effect where all of these, dust specks are forming planetesimals, which form, maybe 3 or 4 planets the size of Mars. And if you want something bigger, you have to crunch all of that together in, chaotic and dynamic planet-planet interactions. The good news is once you're able to build about 10 Earth masses of a rocky core, then that rocky core has enough gravitational pull that it can hold on to hydrogen and helium gas. And there's a lot of hydrogen and helium gas that's left around in these disks. So once you reach that critical mass, you very quickly are able to pull on a ton of new material, which allows you to continue to pull on material, right? It's an exponential effect. So once you reach this critical mass, you can very rapidly become a gas giant by pulling up and sort of hoovering all of this hydrogen and helium that's still within the disk. And then you've made maybe a giant gas giant planet. You've made a couple of rocky planets, but after about 10 million years or so, the gas in the disk starts to disappear. It can start to disappear in multiple ways. If you have a giant planet, that giant planet can eat up a bunch of the gas. But also the star, the light from the star will begin to hit the gas disk. And because the light has a lot of energy, it carries a lot of energy, it will begin to hit the gas and photo evaporate it. So light will come in and send these particles of gas flying outwards out into the interstellar medium. So eventually, over about 10 million years, you evaporate the entirety of the disk, and you're left with whatever you ended up creating with your planetesimals and your giant impacts. So this is actually why we observe more small planets than large planets. And you guys clued into this when we asked the poll question, but there are very few planets that can reach that critical mass that you need for runaway accretion to form an enormous, Jupiter-sized planet before the photoevaporative effect blows away all of the gas in the disk, right? So we see a lot more rocky and Neptune-like planets because it takes a long time for those giant, sort of planetesimals to crunch together to form a core with 10 times the mass of the Earth, so that you can go through this runaway accretion effect. So I've just, dumped a bunch of new information on you, and I've told you to accept it at face value because allegedly I'm an astronomer who's paid by NASA to know these things. But this is my favorite part of the talk, is actually going through and showing you a lot of the pictures and the observations that that have been taken with telescopes all across the world, some of which you can take yourself if you want, that back up all of the stuff that I just told you. So let's start. And this is really why this field is my favorite of all. With other fields, for example, black holes or first light galaxies or all of these cool and very big concepts, right? There are a lot of key steps that appear to be missing in our understanding of them. But for star and planet formation, although there's a ton of open questions, there's a lot of really nitty-gritty and interesting details to sort of dig into. For each of these key steps that I've outlined, we have some pretty strong observational evidence and some really beautiful imagery to back it up with, right? So like I said, for these dark cloud cores, we have observations with radio telescopes of these giant diffuse molecular clouds in our own galaxy. At the stage of gravitational collapse, we can go out and observe star-forming regions where we can see this effect happening. Here you can see an edge-on flared disk that has just ignited a protostar, which has a huge outflow along the axis here. And then here you can see even the shadow of a planetary disk around this star. You can see a debris ring where all of these planetesimals are coagulating into newly formed asteroids and planets. And then at the end here, right, we can literally, for a very small amount, we can go out and take pictures of the resulting planetary systems. So if we start with that molecular cloud phase, this was an image produced by the European Southern Observatory's Very Large Telescope. And this is a molecular cloud called Barnard 68. You can see just how dense it has to be. I mean, there's millions of stars in the background here, but because this cloud is between us and them, all of those stars disappear. All of that light is swallowed up by this diffuse cloud of future planet-making material. Similar here, if you go to radio wavelengths, you can see these massive cloud cores that are, very diffuse and, give you a sneak preview, very diffuse and billowy, right? Where these will eventually condense down into very large stars, the sort of bright blue stars that we talked about at the beginning. Along the next step, once you start to have those clouds condense down onto each other and you see all of those interesting feedback effects from the newly igniting stars, you can see these beautiful star forming regions. So these are from my office mate, actually, Natalie. And these are Hubble Space Telescope and Spitzer Space Telescope images of a star forming region called NGC 1333. So you can see here a newly formed star is, erupting with this cascade of hot hydrogen gas that's being shocked along. You can see, we're just seeing sort of an open region of this dark and dense cloud out here that's blocking all of the background stars. And here we can see a lot of this, sort of wispy filamentary stuff is shocked iron and magnesium gas within these star forming regions. And there's a particular star forming region that is very, very good to observe if you're an amateur, and it's coming up at least, yeah, for the northern hemisphere. It's sort of rising in the winter, um, and that's the Orion star forming region. So this is one of my own amateur observations of Orion. And on the left here is, or on the right here is the Hubble Space Telescope version, slightly zoomed in. But Orion is one of my favorite targets. I run the campus observatory at JHU, and so I do a public outreach for kids, and it is an absolute blast to show your friends and your family, and for me especially to show the public a star forming region like this, seen through the eyepiece of a telescope. Um, what's really interesting about Orion though is that you have these four or so very massive blue stars at the center that are called the trapezium. And those stars are responsible for most of the illumination within this region, right? They're literally responsible for, carving this massive cavity out of this once diffuse and inert cloud of gas and dust, right? So all of this, rippling that you can see along these images, right, is due to the solar winds of just these four stars. And what's very, very cool is that you can see that those four stars are having an effect even on the protoplanetary disks of the nearby smaller stars. So you can see here, there's a protoplanetary disk, but there's this huge bow shock to one direction where it's facing these bright and massive stars at the center here. So there's a way in which, and this is one of the complexities that still needs more observations and more theory to understand, but there's a way in which where your star forms within a giant molecular cloud, whether it's nearby to more massive stars or not, could have an effect on the kinds of chemistry that you see within a protoplanetary disk, the kinds, the amount of the disk that you have, and therefore the amount of planets you're able to form. Whether these stars going supernova could preclude life on, all of the stars that are nearby it, right? So there's lots of interesting complexities, all wrapped up in a very nearby and very recent region of star formation. So we're pretty lucky to live at a time in the Earth's history where we can observe the Orion Nebula so close by. If we zoom in even further, these are protoplanetary disks as seen in radio emission with the ALMA telescope in Chile. So this is a huge array of radio telescopes. And if they look a little fuzzy, that's because this is some of the highest resolution imaging that you can do, right? I mean, this is super, super high resolution. And when this was published a couple of years ago, I mean, this was mind-blowing stuff, especially for astronomers working on these systems. Because I showed you from the Hubble Space Telescope, if you actually zoom in on the protoplanetary disk way back here, this is what you're seeing, right? And that's with one of the best, most stable space telescopes in the world. You're seeing this sort of oval. And if you go to the ALMA images, I mean, wow, you can see individual rings and gaps in these systems. You can see the hints of spiral arms here in the outer regions of the disk. And all of these are indicative of that giant planet formation process that we talked about, right? Where you have a massive planet form with a core 10 times the mass of the Earth that begins to sweep out these regions of the disk as it hoovers up all of that gas that's left over. So you're seeing the cradles of planets right here. I mean, this is part of the reason why I became an astronomer when I did. If we go to a more conventional telescope, into an optical telescope, you can observe much similar things, but this time, as opposed to seeing the dust in the midplane of the disk, which emits very cold, microwave and radio wavelengths here, you can see the scattering light off of the surface of the disk. So these disks appear more fluffy, but that's just because the light here is you're seeing a different portion of the disk than you are with the radio wavelengths. And in particular, you can see these, beautiful mid-planes here, the flared aspect of these disks, this one especially. But you can also see some of that same structure that you see within the ALMA images, these gaps and rings that might be indicative that there's some forming planet within the disk. So these were from also from the European Southern Observatory's very large telescope. Here's some of my favorite examples, again, of disks. This one in particular, because it has this beautiful double spiral feature. And it's unknown how you generate such a feature. Some people think maybe if you have a planet sort of at the end here and the planet's orbiting, it can trail the spiral around behind it. And then here, if you notice, there's a sort of a lump at the end of this ring here. So maybe that's an overdensity that could be forming new planets. Or maybe it's a material that a already formed planet has gathered around it. And then this one is gorgeous. This is just these really well-defined rings in this system, which seem to indicate that there's probably a pretty mature planet that has cleared out these gaps and sort of shaped the rings here. So this is another one of those, looks kind of fuzzy, especially to the public, but this was take a step back, go for a walk, get coffee with your colleagues when this image came out. So these are direct images of two protoplanets, right, within a circumstellar disk. So you're zooming in even further, right, and you're seeing two planets about the size of Jupiter that are gathering this material around them, clearing out this cavity, and are only a couple of million years old. And this is the one system like this that we know of so far. But I'll tell you right now, and I can't show you these results, but we're looking for more of these systems with JWST. So hopefully expect some fun results in this ballpark. But for now, I mean, we still love this. This system is the poster child of the field because it's the one that we've really been able to definitively nail and say, I mean, here's planet A, here's planet B, or B and C. Here's the disk, right? It's all resolved. It's all, distinct from one another. It's just gorgeous. And here's a nice, artist's interpretation of what's going on here. The really cool thing about this system, and something that I've worked on, is that if you observe this system in particular wavelengths of light, where hydrogen emission is the strongest, you can see this runaway gas accretion effect that we spoke about. You can see the hydrogen gas falling onto the surface of this newly forming Jupiter-sized planet. This is for much of the reason that a lot of amateurs observe, nebulae and narrowband filters. And this is an equivalent filter. This is the hydrogen alpha filter that you might go and take a picture of a supernova remnant in. But this filter selects out only that hot emission from this hydrogen gas as it falls onto the surface of the planet. And you can see while the rest of the disk glows with very cold infrared emission, the planet is the only thing that's super bright here. And that's because it's physically pulling on this new hydrogen gas and heating it up as it hits the surface of the planet. So we can also observe these planets orbit within their disks with very high precision instruments. So you can see the orbital motion since we've discovered the planet in around 2018, I think. And with this super precise instrument, you can see, this difference here as the planet is orbiting within the cavity. I mean, once we have, a more complete picture of the orbit, that will tell us a lot about, how the planets are clearing the gap, how they might interact with the rest of the material around them. And then this is the last on this particular system, but this was in the New York Times, a huge press release earlier. I think it was earlier this year. It might have been earlier last year. This is, like I said, the ALMA radio telescope as of around 2015. But if you upgrade that telescope a little bit and you use some higher resolution settings and some astronomical wizardry, you can get this image in 2022. And this is resolving the planet in radio emission from this outer edge of the disk here. And if you notice, the planet itself has this sort of extended region of emission around it that's glowing in the sort of same wavelengths as the rest of the disk. And this is evidence for a circumplanetary disk. So this is a disk around the planet within the disk around the star. It's like a nested doll kind of situation. But this is how we think planets like Jupiter get their moons, right? So Jupiter has 4 Galilean moons that all are relatively, spherical, that all orbit in the same plane around it. And we think that if you have a massive enough planet that can collect its own disk of material around itself, it can, like a mini solar system, form a system of regular, spherically or circularly orbiting moons like Jupiter did. So this was mind-blowing when this result came out. So if we want to then go and the disk is blown away and we're looking at old stars and we want to observe the fully fledged solar systems, one of the ways we can do that, and the way that I'm a particular fan of, because it's what I do in my research, is called direct imaging. So this is the seeing limited, PSF of a star. And then if you use what's called adaptive optics to correct for the Earth's atmosphere and to reach the diffraction limit of your telescope, this is sort of what that looks like. And then you can use an optical piece called a coronagraph to block out the center of the star. Right, so you see here, this coronagraph is a physical optical element that you put in front of your telescope. It blocks out most of the starlight, leaving this sort of residual halo. And then you can do some post-processing. You could imagine using a high-pass filter to just remove this diffuse extended emission here, and you get a planet detection right there. So this is a similar schematic here showing the seeing to the adaptive optics, and there's a hint of something there, and then you put a chronograph in, and the little companion is very bright. So this is a technique that's mostly been pioneered from the ground because you want a large telescope aperture to get the most resolution possible, so you can see close into the star where the planets are. And this is one of the most enigmatic results from this detection method. It's a system of 4 planets that we've observed since around 2008. You can see in that time we've been able to catch them orbiting in this beautiful orrery fashion. And hopefully I'll get to, in the last portion of the talk, I'll get to show you some of the latest results of doing this technique with JWST. So that's the little teaser for the very end. But there's another way of observing planets, and it's called the transiting method. And so when you have a planet that by chance passes between the observer and the star, it can block out a portion of the star's light. So if you observe the brightness of the star over time and you see this characteristic dip as the planet passes in front of the star, you know that there's a planet in that star system. This is fun because bigger planets obviously block out more of the star's light. So this method tells you something about the physical radius of the planet that you're observing. The other cool thing about it is that it's something that you can do with amateur telescopes. I mean, the first transiting event back in 2000 was observed with I think an 8-inch telescope in the parking lot of, a astronomy department out in Colorado. So this is something that you can do on the ground, even from your backyard. This is a transit that I observed from the middle of Baltimore City. Right, and it's still a nice clear signal. And there are lots of amateur observers who have tons of great tips on how to observe these events, and also really nice and easy to use programs like AstroImage that you can extract these light curves from your series of images. So that brings us to the very last portion of the talk, which is just bragging basically about all of the the wonderful results from JWST. So a lot of really fantastic stuff is happening at Space Telescope Science Institute these days. We worked for months and months to, to commission the observatory and to make sure that it was science ready. It's gone through tons of delays, but it really has proved, I think, to be worth the wait. You probably have seen one of the first images that came out of the telescope was this beautiful image of the Carina Nebula. And this is a star forming region, right? This is the start of that process that we've been talking about, seen at, super high resolution and high sensitivity. You have this, central cavity here that's being photo evaporated by the hot winds from those bright blue stars. You have all of this wonderful diffuse gas and dust out here, and thousands of newly forming protostars. And interestingly, if you zoom in on this picture, you can see those bow shocks from those newly ignited protostars all over the nebula. So with this one image, you're really capturing just the birthplace of hundreds and thousands of newly formed solar systems. There was also this spooky Pillars of Creation that was released recently. So this is another really great target for amateurs. You can see my 15 minutes of the Eagle Nebula in an H alpha filter here. But you compare that to JWST, and what you're really observing here is emission from the dust itself. So in the optical, you're seeing emission from the stars that are being blocked out by the dust, but in the infrared, you're seeing the dust itself, and it's just spectacular. This is my personal favorite. It's the Tarantula Nebula. And if you zoom in and look at even longer wavelengths of infrared light, you can see this is emission from those dust grains, the silicate and the iron dust that will fall onto a new forming disk and then create the pebbles that go on to generate planets. So short wavelengths, long wavelengths, showing two really different sort of aspects of this planet, the star forming region. I'll go really quickly since I don't know if I'm running over time, but here's an embedded protostar and its outflow, right? So these are sort of bow shocks of gas as the star turns on its ignition key, basically, and starts fusing hydrogen. And this is a really lovely observation, but it's even lovelier if you take a spectrum, you split the light from this star into all of its component wavelengths. You spread those out because what you can see is absorption from water and from ammonia and methane, CO2, and from the dust here. But you can also see absorption features from these very complex organic molecules that are there even at these early stages of the disk formation, right? So these molecules are some of those that could go on to eventually, seed life within this new solar system. And they're present even if you look at the earliest stages of the star's lifetime. And then this was, I think, the past week or past couple weeks, but this was another favorite of mine. If you look at this nebula from the ground, this is what you see. You see a really lovely mid-plane in this disk, and then maybe this sort of hourglass shape here, right? As this material is falling onto the disk and onto the newly formed star. But you point a multi-billion-dollar space telescope at it, and you get this kind of image, right? You still see that beautiful mid-plane, the flared structure of the disk, but you see here that conservation of angular momentum, bringing all of this material down onto the disk itself in these beautiful, beautiful wisps and filaments. So this was breathtaking too. Yep, and if you zoom in, right, that's the conservation of angular momentum for you. There have also been some lovely results in the planetary transit regime. So this is a light curve of a planet from JWST, and really the thing to note here is that the precision is just really, really impressive, right? This light curve is very stable So there's not a lot of noise here, and you can really very sharply determine the radius of this planet. And if you look at different wavelengths of light, you can also see different molecules in the planet's atmosphere absorbing more or less of that light. So that was this result that was published recently, where we saw carbon dioxide in this exoplanet's atmosphere. And then this is one of the things that I worked the most on the past year or so. And this is pointing a very, very sensitive telescope at a very bright star. We threw a chronograph in there for good measure. But this is the super bright star in the HIP 65426 system. And if you throw the chronograph in and you do that post-processing that I was telling you about, this is what you see, which is a resolved image of a planet about the same size as Jupiter, but around 7 times heavier. So this was a result that was published this past September. And it doesn't look like much, but a lot of time and energy went into this beautiful flower right here. It looks like a weird flower shape, mostly because of the way that the light diffracts around the hexagonal edges of JWST's mirror. But you can imagine that this shape is just the characteristic point spread function of the telescope. So yeah, that's been that. I did what any good amateur astronomer would do, and took the data from our paper and tried to make a pretty 3-color image. And I think the cool thing about this is that there's some background stars within the image too that you can see, and those are all blue because they're very hot. You can imagine like a blowtorch, right? The center of that flame is blue, but your campfire is red or white. So the background stars are all blue and the planet is white. So that's about that. And while I didn't present it this way, I think one of my key takeaways is that astronomy is really a backwards science most of the time. A lot of the time, we as humans make a new telescope, observe a new thing, and we have to come up with a theory in order to explain what we're seeing. So everyone should keep observing, right? Thank you, guys.